Please give a talk.
Yeah, thank you, the organizer. Thank you, Chris, for the kind invitation. So my topic is a bit out of the scope of this workshop, but some applications will be very close to this area, I suppose, and maybe it's opportunity to further collaboration. I will talk mainly about fibers and nanostructures and the fibers. So I will start from the very basic knowledge. Refractive index is the ratio of speed of light with the speed in the medium, speed of the wave in the medium. Yeah, and for different materials in the visible spectrum, the refractive index changes from 1 to about 4 for silicon and germanium. For glass, it's about 1.4, 1.5. And if we will illuminate light from the more optically active medium, so from the medium with higher values of refractive index to the media from the lower values of refractive index, under some angle of incidence, we will have the total internal reflection. So you can see here that light is partially reflected and transmitted, but under some angle, the light do not transfer to the second medium. So it's absolutely totally reflected, and this regime is called total internal reflection. We can see it as a laser put it in the water or glass, or practically it may be seen if you dive very deeply and look up. So you will see only a circle of light, or other will be darkness. And the reason is again total internal reflection, this cone of the available angles corresponding to the transmittance of light. All other is reflected, so light doesn't transfer to another medium. Okay, and based on this principle is realized in optical fibers, which is usually composed of glass in the glass. So this is some, let me say, silica with doped core, and the refractive indexes may differ very, very slightly. So just in several thousands. So for instance, here I will consider the refractive index, the fiber with refractive index of core 1.454, and the cladding will be 1.45. So just 4,000 is the difference of refractive index between core and cladding. But this allows to hold light propagation only within the core, and light can be transferred very quickly and at a long distances with minimum losses. Now this is like it looks for some different simple commercially available fibers. Okay, and fibers are very important for telecommunications. Indeed, this is the main carrier of our information. Such a very giant subsea fibers are under Atlantic Ocean and other oceans. This is only the map of subsea fibers. Each such a fiber can transfer terabits per second. So this is a giant volumes of information, and indeed our information is transferred via fibers, mainly not via radio, GPS, or I don't know, antennas, for instance. Okay, and there are some other applications, usually some fiber-optic sensors and detectors. So it's important everywhere, in every closed, limited space, in airships, in cars, in different technical engines, and also in the medicine, it is called as endoscopy. So such a fiber with, for instance, camera or with some other device can be put it in any holes. Indeed, for instance, to study the stomach, yeah, which is very popular, and it's important because it allows to see the in vivo picture in the real-time region. It's much more effective for the correct diagnosis in comparison with many analyses which give you just indirect picture. Okay, but there are, despite all this advantage, despite the ability to transport light for very long distances and ability to reach very closed, even in vivo spaces, there is one disadvantage. If I illuminate plane waves on the fiber and face it, what is the efficiency? I will call it further encoupling efficiency. So under encoupling efficiency, I mean the efficiency of the transforming of the incident plane waves into the guided modes of the fiber. So if I illuminate under the normal incidence, I have almost ideal efficiency, encoupling efficiency. So whole intensity of my incidence light transforms into the guided mode of the fiber. But under oblique incidence, this efficiency rapidly decreases, such as under the incident angle of 15, 20 degrees, we have the so small values that practically it's irrelevant. And of course, it significantly limits the applications for detectors, spectroscopy, endoscopy, application of the fibers. So practically, it means that fiber can see only directly in sharp contrast, for instance, to the human eye, which can see the objects from wide range of incident angles. And of course, this is a big limitation. And how to overcome it? So we are not the first who proposed to do it with so-called today lab on fiber concept. So idea is to structure the surface of the fiber. It can be structured inside fiber, around, so at the side walls of the fiber, but we are focused on the fiber tip nanostructuring. So here I would like to present one of the most successful implementation of fiber tip nanostructuring with plasmonic array of nanodots. So here the authors put the periodic subwavelength array of such a gold nanodiscs. And here the result the experimental result of the measurements. So orange dots correspond to the bar fiber without nanostructure, and blue dots corresponds to the fiber with plasmonic nanodots. So one can see that coupling efficiency is greatly enhanced. So I would like to notice that here we have the logarithmic scale. So this is multifold enhancement for the angles more than 25 degrees. But at the same time, the coupling efficiency is still very low, 10 to minus 5 and around 10 to minus 6 at the large angles where the coupling efficiency is especially difficult to achieve. And we formulated the challenge for us to achieve a big coupling efficiency, namely a % level of coupling efficiency. First of all, for large incident angles, where this is the most difficult challenge. And here I have to mention my colleagues. So this research was proposed by Professor Markus Schmidt from Leibniz Institute of Photonic Technologies in Jena, Germany, and Professor Yuri Kivshar from Australian National University. They are famous and great specialists in fiber optics and nanophotonics, respectively. And Yuri invited me into this project, especially to analyze the process of nanostructures and propose some relevant designs. And our main idea is the following. We propose to put such as a first step, such as axial-symmetric concentric rings made from the dielectric material. So this material has relatively high refractive index and negligible absorption losses. This is first great advantage in comparison with plasmonic nanoparticles, which, as it is well known, have high absorption losses. Here we don't have at all. The idea is that such a nanostructure acts as a diffraction grating, and its first diffraction order coincides with the fiber axis. So we just would like to send the light into the first diffraction order mainly. So in such a sense, we send it along the fiber axis, leading to perfect transforming of plane waves into the guided modes, so to the perfect in-coupling efficiency. Another advantage, practically important advantage of this structure is that it is almost independent on the incident polarization of light. So it may be T or TM or some circular elliptical, doesn't matter. It is actually symmetric, so it is independent on the azimuthal angle of incidence. So it doesn't matter from this side or from this side, light goes, important only the angle of incidence, the angle between normal and the wave vector of the light. So this is our idea. And I have to propose to introduce several definitions. So first of all, this is effective coupling area related efficiency. So we define effective coupling area as the ratio of the power of the guided wave measured inside the fiber divided per the intensity of the incident light. And AM here is the area of the mode. So practically it is very close to the area of the core, because the light mainly confined by the core walls, by the interface of the core and plane. However, this definition suffers. It depends on the incident intensity of light. So changing the intensity, we can obtain very different values of effective coupling area efficiency, and we propose normalized fiber and coupling efficiency. So in this case, we divide the effective coupling area related efficiency per the same value, but for bar fiber. In such a way, we eliminate the intensity of light and obtain the ratio of power measured inside the fiber. For nanostructured case, divided by unstructured case. Indeed, the maximum possible power is defined as the power measured at the bar fiber exactly under normal incidence. Obviously, if we add some nanostructure at the top of the fiber, we obtain maybe small, but at least we obtain some additional reflection. So total intensity cannot be bigger than in this case. So it means that at zero angle it will be 1, and for further angle it will be lower than 1. We also introduce average fiber and coupling efficiency, which is defined as follows. And practically, it gives you the average value in coupling efficiency in the range from θ1 to θ2. So if you take this angular range, approximately at any angle in this range, the coupling efficiency is equal to this average value. And finally, to compare the outperformance of nanostructured fibers, we introduce boosting factor as follows. We just calculate the ratio of measured powers at any angle of incidence. Let me first introduce a toy analytical model. It is based on the overlapping integral between the tangential components of electric fields of the eigenmode of the fiber and of the incident light scattered by the nanostructure. So this is mode, this is scattered by nanostructure light. So the expression for the field of the mode is well known and can be found analytically. It's not the problem today, of course. How to find the scattered by the nanostructure field? It's more difficult question, but here we propose very simple model which may qualitatively correctly describe the results. So first we assume we find the transmitted field without nanostructure. So imagine that we don't have nanostructure, then transmitted field is as follows. And then we multiply it by some phase factor. And the phase itself introduces as such a step function where each non-zero step corresponds to the arrangement of the rings. So I show the cross section now. Yeah. And in such a way, then using the corresponding normalization, I can find this effective coupling area. Divided by the coupling mode, I obtain normalized coupling area, and here I can define it. So then I can change the width of the rings, the height of the rings, the period of the rings, and find the best design. Such a code realized in, for instance, MATLAB. In MATLAB, calculates the angular dependence of the coupling efficiency just for several seconds, so it's easy to check hundreds of thousands of designs and choose the optimum one. Then we switch to the fabrication of the structure. The rings are made from the silicon nitride. This I don't remember, but refractive index is close to 2. So 1.94 or 95, something like this. And it was done via complicated many steps processes based on electron beam lithography, with following ion beam etching and resist removal. And finally, we obtain the following structures. So here we take several single mode fibers, and the first one we left unstructured, while on the other ones we manufacture the nanostructures with different number of rings. Now this is like it looks different scales. I think here at the top this is 50 microns, here it's 20 microns, and here is maybe 2 microns, I think. Okay, and then we just measure it. We illuminated the Gaussian beam at the unstructured fiber tip and measured the power of guided mode inside the fiber for further calculations. And this is the central result of this work. So here we can see the coupling efficiency calculated experimentally and numerically. This gray dashed line corresponds to the bar unstructured fiber, so fiber without nanostructure. White color lines corresponds to the fiber empowered by the different number of concentric rings. And we can easily see that at large angles more than 60-65 degrees, we have a great enhancement of the coupling efficiency, several orders of magnitude. Okay, then we calculated the coupling efficiency within some angular range. Yeah, in some sense, this is close to the average in coupling efficiency. But what we have shown here is that for the Barn structured fiber, to have, for instance, the number of coupling efficiency close to 10⁻⁴, the angular range must be more than 70-80 degrees, depending on polarization. While for structured fiber, it can be just 10 or 15 degrees to achieve the necessary level of coupling efficiency. And that's why we are interested in such an application as single photon collection, or the analyzing on for instance, scattering and the single molecules, which is useful for biophotonics and vivo imaging as well, endoscopy, optical coherence tomography, and so on. And this work was published in ACS Photonics Journal and was put at the front cover of the October issue 2020. And I think it may be summarized by this figure, where we have shown that nanostructured fiber leads to the several, at least 4 orders of magnitude in comparison with bar fiber at large incident ends. So the structure here was implemented using electron beam lithography. It was very difficult fabrication process, but in principle it may be done with silicon nitride in this work. And this work was also featured by Optics and Photonics News Journal among top 30 the most important and exciting works in optics and photonics. And then we went further. So our main problem was the difficult fabrication process, which of course limits the development of this field. And my colleagues from Leibniz Institute proposed the fabrication based on direct laser writing. In this case, the structures can be produced within just a minute with perfect, very precisely, very quickly. And even more, we can control the width, the height of each ring, and the distance between any 2 neighboring rings. So it, as I will show further, it gives us additional degree of freedom. One like ambiguous point is that it can be done with such material as polymers. And polymer, especially we use the polymer with refractive index 1.55, while as you can see, as a refractive index of the core is just less than 10% lower. So it was a question for me if it will work with such a low index materials. But yeah, it works almost so. It works pretty good, making additional degree of freedom and much easier fabrication process. So first of all, we studied the single pitch gratings. So it means that all rings are the same, maybe except central ring. And changing the period, for instance, maybe the width of the ring, we can shift the resonance of the best coupling, indeed shift the angle corresponding to the first diffraction order, at any angle of incidence, 40, 60, and less efficiently, but more or less okay, at 75 degrees. Here, I would like to notice, especially in comparison with previous figures, that indeed wire fiber at the level 10 to minus 7, the signal from wire fiber is compared with the noise level. So 10 to minus 7 is already noise level. So as from simulation, we obtain the following picture for wire fiber shown by these gray dashed lines, but experimentally we can measure up to this level 10 to minus 7. Okay. Then we did the double pitch gratings. So it may be considered as the sum of two nanostructures, two types of nanostructures with such a double period, and it leads to the emergence of the second diffraction order of the second resonance here. So we can achieve we can enhance the coupling efficiency at separate angles, as it's shown here, and verify it pretty well experimentally. So here, the previous slide, solid line corresponds to the experimental measurements. Dashed line corresponds to the simulation. Then we propose the aperiodic nanostructure. It is not seen here, but each, at least first 4 rings have different height, width, and the distance between them. So each parameters are different, slightly different for each 4 rings. Each 4 rings, I mean, the first 4 rings gave the most of contribution to the coupling of light, of course, because they're located in the vicinity of the core. So other rings are not so important here. And we can see that the angular front is almost flat, not flat, but more or less close to flat, for instance, in comparison with this figure. So it means that at any angle of incidence, we will have approximately the same level of coupling efficiency. Of course, it will be lower than here at the resonance, but higher than at any average angle, at any arbitrary angle. Say. Then we have compared the different structure between each others. Yeah, and first of all, we calculated the boosting factor. So the ratio, boosting factor means in how much times the nanostructure fiber operates better than the bar fiber. And we can see that for the incident angles more than 20 degrees, usually from several hundred to several thousands or even 10,000 times for any nanostructure, single pitch, double pitch, periodic, aperiodic, etc. Another point is to show the angular range, angular intervals, where the efficiency of where the coupling efficiency is at the level more than 10 to minus 4. And we can see that for bar fiber, it's about 10 degrees, while for single pitch gratings, it may be enhanced at some corresponding angular intervals, about 40 degrees, 60 degrees, 75 degrees. But of course, the best performance is done by double pitch and aperiodic gratings, covering almost whole angular interval. Yeah, I have also forgot to mention that especially at single pitch gratings, we achieve the percent level. So at the maximum level of coupling efficiency is several hundred, so several percent in comparison with bar fiber at normal incidence. Okay, and finally we have calculated average in coupling efficiency. I have represented it as a color maps. So some arbitrary point here, yeah, means shows the average coupling efficiency between the angles θ1. θ1, this is a it's shown here. Yeah, this is this horizontal axis, and θ2. So θ1 is initial, θ2 is final angles of incidence, and within this range, the coupling efficiency is shown by these colors. And what we can see, so for instance, this figure corresponds to the bar fiber. Yeah? We can see this coupling efficiency is okay only at the very small angles, typically less than 10 degrees. We can see this orange and red zones corresponding to the coupling efficiencies, let me say more than 1%. For single pitch gratings, we can easily see that it works especially well in some limited angles near the designed resonance, so like 40, 60, and 75 degrees. We can see that there are such a two resonance for double pitch gratings, which also was our goal. And for the aperiodic structure, the distribution of average coupling efficiency is more or less homogeneous, which means that also we have some average values of coupling efficiency the same at any angle in any angular intervals at the level about 10 to -3. Here left columns correspond to the simulation, right to the experiment, but they are more or less coincide. And yeah, this work was recently published just in the beginning of this year in Applied Physics Reviews journal. Currently, we are preparing the review about the nanostructured fibers for this journal, and I would like again to thank my colleagues, mainly the group led by Professor Markus Schmidt from Leibniz Institute of Photonic Technologies and Professor Yuri Kirshar from Australian National University, and Andrei Bogdanov from China. And yeah, taking a few minutes more, being now in Ukraine, I would like to mention that Russian invasion of Ukraine is still going, and it's like the city center of my my home city, Kharkiv, was looked in May, I think, previous year. This what was with our university, especially I studied in this lecture room. This like looks my home building in Kharkiv, and I asked to make all the possible what you can do, from each of us can do, to stop this, especially to support Ukrainian scientists and people, and to sanctionize Russian scientists, why we should do it, and what's happening now. I briefly presented is via my social networks and can be found here. Many thanks for your help and for your attention. I'm stop here and ready to answer the questions.
All right, so thank you very much for very inspiring talk and excellent results. So I will ask audience about the questions. Okay, maybe I will ask in that way. How deeply you go into modeling of your structures? How fundamental is your model?
So yes, thank you for the question. It's really important and not so obvious. So I will maybe return here. So we have maybe a better figure now. So we did that in Comsol multiphysics. via wave optics model in frequency domain. And the idea was the following. We considered the axial symmetric structure. So we put the central axis and simulated only the one cross section. So this is therefore it is two-dimensional simulation, which makes it much simpler and faster. Sure. As far as the structure is actually symmetric, we can then rotate it over 2 pi and obtain the full picture. So the width of the structure or the distances are exactly the same as the fiber. So the cladding is totally, as far as I remember, somewhere about 120 microns or something like this. And we did full simulation, of course, so everything is absolutely correct. The mesh is perfect, which was checked many times by the different tolerances. And the main point is that we see the good coincidence with the experiment. So we simulate the incidence from the one port, exciting plane waves, or it can be Gaussian beams as well, and calculate the transformation into the fields of the guided modes checked by the other port. So it's not so, let me say, trivial maybe, but is fully described in the supplement. This method is fully described in the supplementary of this article. Yeah, and also there are several trick steps. Trick steps also described there, because we should respectively normalize the fields if we transform from Cartesian to cylindrical coordinates. So some additional factors should be applied, but yeah, that's all. Yeah, so we applied 3 methods, this analytical model, to achieve the approximate designs, very approximate. Then these approximate designs were optimized numerically in console. And then we came to the experimental fabrication and measurements. And in general, the calculation of angular distribution of such a distribution for one design, but for whole angular range from 0 to 90 degrees, takes about 2-3 hours in console using just my computer. It's not something very powerful, but yeah, it's powerful, but it's not the fastest.
All right. Okay. Thank you for your answer. Do we have any more questions from Zoom participants or from from the audience here? All right. If not, thank you. Let us thank the speaker again.
Thank you. Thank you a lot again.
Okay.